So what is it that we really do when we do a computer experiment on dynamics and know nothing about it other than that? What we do is we take a trajectory, start at some point, x0, and let's assume we have a continuous time flow. For discrete map, it's almost the same. Then Perron-Frobenius or determinism tells us I get someplace at time t. So what's happening is that trajectory is tracing out something. I mean, the state space, this particular point is doing something, going all over the space. And I can now define a function called rho x0, which is limit t goes to infinity 1 over t integral of. So if I'm on some initial point, I trace all of its future by integrating over whatever it can be and divide by t. I am producing a time average of what this trajectory is. And that's what computer does. The only thing extra computer does is it doesn't actually evaluate the delta, but it's generating errors of integration as you go along. So it's using somewhat smeared out thing. Now, what do I actually do to describe my density function? I can only do it to finite resolution. So what I do is I box it in little regions, like this one, mi. And then I can compute the probability that I'm in that region. So I can compute d mu I equals limit t goes to infinity of total time versus the time spent in the box. So every time I enter, I get a little interval, and I get another one when I re-enter again, t1, t2. When I sum all of them, I get total time traversing the box. And that's actually how I numerically compute the likelihood to be in some region. I run my computer. I divide the space in little boxes. If I do this cleverly enough, I'll only make boxes in the region which I visit and not boxes where I have 0 all the times. And to the coarse graining resolution, this is the probability of getting there. And then I'll make boxes smaller and make some estimate of what the measure looks like. So even though this looks horrible, it's some delta functions and you know what to do. This is what it really means. Is time spent. So this is now a numerical thing, and I probably won't make you do it, but if you do it yourself, if you actually do this, so take a non-attractor, which is very simple attractor, and you do this calculation, which is very simple because it's 2 dimensions, so it's easy to box it and do it, you'll find a horrible function. Rho will be a function that looks singular every place. You look at any neighborhood, as you resolve the neighborhood, there'll be all kinds of features on it. And in dynamics, we understand why. I mean, we can explain these features. So most of the mathematics is concerned about what these measures look in the limit, and the statements that they prove is about continuity of the measure. They say if the system is ergodic in every little open interval, there will be some measure. But if you actually try to work with this, this is a nightmare. This is useless. So this is the reason why I personally developed periodic orbit theory. It's totally insane to look at what happens at infinite time when I have finite time information only. So what the periodic orbit theory, which you already know because last week I explained all of it, more or less, does is it says, instead of being an idiot and running this stuff just forever, think and realize that you can partition, you can use dynamics to subdivide the state space and use that partition, and that partition happens to be done in terms of periodic orbits. And those are very naturally described in terms of Perron-Frobenius operator, as I'll explain. So it's a glorified counting matrix. Last time it was called transition matrix, but now it works on smooth things.